Hi folks, today we're going to talk about covalent bonding. There's a lot to cover here. I'm going to go through it as quickly as I can. So just take some notes along the way, make sure you pause the video and get down what you need. Okay. A couple of examples. Don't need to write this down, but just kind of have an example. Who wants to hang around with Bill Gates? Why do you want to hang around with him? Why would you hang around with the presidential candidate? I'm recording this in an election year, so we're seeing a lot about presidential candidates. Who appears to be their friend and why? Pause the video, see if you can come up with that. Alright, here's your second example. You have a girlfriend and boyfriend, or an employer and an employee. Why do these people stick together? Why does an employer continue to hire an employee? Why does an employee stay there? Why do a girl and boy stay together? See if you can figure that out. I guess that second question was kind of hard. But anyway, presidential candidate and the staffer is hoping that he or she's going to get a job if this person gets elected. Same thing with Bill Gates. If Bill Gates goes and gives you money, that's why you hang around with him, because he's got bunches of money to throw around. Versus a boyfriend and a girlfriend. Well, the boy feels like the girl cares about him, and so he feels loved. And the girl feels that the boy cares about her and provides for her, and hence she feels loved. Or the same thing in an employer and employee. An employer feels that the employee is doing a good job, and the employee feels that he's being paid. So they stick together for that reason. In one case, you have a sharing of stuff going on, and in the other, one person's gaining, the other person's losing. Okay? If Bill Gates is giving you money, he's losing it, you're gaining it. But in the case of the boy and the girl who are sticking together, they both are gaining something out of the relationship. So, chemicals work that way too. In some relationships between chemicals, one atom gives while the other takes. We call that ionic. In some relationships, they share. We call that covalent. Alright, so remember the octet rule. Atoms tend to gain, lose, or share electrons in order to obtain the electron configuration of a noble gas. Today we're talking about sharing. And the thing that we are sharing are the valence electrons. And remember, these are the electrons that are furthest from the nucleus. The electrons that are in the highest principal energy level are our valence electrons. So remember, ionic bonds are between metals and nonmetals. Metallics are between two or more metals. Covalents are between two nonmetals. And again, that's what we're focusing on today, are two nonmetals. So if you see a metal and a nonmetal bonded together, that's ionic. Don't even think about covalent. If you see two metals bonded together, they're metallic. Don't even think about covalent. The time you're going to think about covalent is when you have two nonmetals. So what are the nonmetals? They're the ones in blue. Now again, the noble gases, way over here on the right, the noble gases probably aren't going to bond. Right, so you're talking about all these blue guys, plus over here, remember you've got hydrogen sitting way over there. Alright, it is also a nonmetal. So we're going to have to worry about those. Right. Also, some of the semi-metals sometimes get into the act, like boron will get into the act and silicon will get into this as well. So sometimes you have semi-metals or the metalloids thrown in as well. Alright, so what is a covalent bond? They are shared electrons between two atoms, and it's a shared pair of electrons. So every bond is made up of two electrons. So for example, if it's two people, one is coming from me and one is coming from you. So if we have two atoms, one electron is coming from one atom, one electron is coming from the other. And there are many things that are bonded by covalent bonds. Paper, plastic, plant matter, water, sugar, carbon dioxide, oxygen gas, DNA, all of these are examples of things that are covalently bonded. So, you need to write this down. You need to write down the definition of a molecule. A molecule is a group of atoms that are united by covalent bonds. Notice covalent bonds. So anything that is ionic is not considered a molecule. Alright? It has to be covalently bonded. Alright? So make sure you get that. A molecule is something that is covalently bonded. A molecular substance is made up purely of molecules. And molecules can be small, like O2, or H2, or carbon monoxide, or CO2, or water. Or it can have thousands or even millions of atoms. If you look at DNA, for example, right? A huge number of atoms, or polyethylene plastic. Huge, huge, huge numbers of atoms. Okay, millions, billions of atoms, okay, that get together to make polyethylene plastic. Okay. So, let's do a shared electron configuration, a Lewis dot diagram for chlorine. Right, so pause the video, pull out your periodic table, and then we'll do this. Right, how many valence electrons does chlorine have? You should have said 7. So we have 1, 2, 3, 4, 5, 6, 7. And then we have another chlorine atom, right, which has 1, 2, 3, 4, 5, 6, 7. Now these two chlorine atoms, chlorine electrons, excuse me, in the middle, those are the ones that are going to be shared. All right, so we can write this many different ways. We can do this as Cl, 2, 3, 4, 5, 6, 7, 8. These are the two that are shared. All right, so this chlorine over here on the right had 7 electrons, and so it had one of these that belonged to it, and this chlorine over here on the left had 7 electrons. One of these two in the middle belonged to it, so these two form a bond. And sometimes we will write this as Cl to Cl. Sometimes we'll write this as Cl to Cl, and we'll put all of the other Lewis dot electrons out here, which is helpful. And each of these lines represents a bond or 2 electrons. All right, how about O2? Again, look at oxygen on your periodic table. You'll see that it is in group 6A. So it, excuse me, is going to have 1, 2, 3, 4, 5, 6 electrons. Well, it's going to go and bond with another oxygen that again is sitting here with 1, 2, 3, 4, 5, 6 electrons. So these 2 electrons are going to form a bond. They're going to be shared. And these 2 electrons are going to form a bond. They'll be shared. So oxygen is actually going to have 2 pairs of electrons between it. So it's actually held together by 4 electrons instead of just 2 like chlorine was. So we could write this as oxygen with a double bond with 4 more electrons out here that are pairs. And you say, well, how many, if I look at the oxygen on the right, how many electrons does it have? Well, it has 2 right here. It has 2 there. That's 4. It has 2 from this bond, which is 6, and 2 from this bond, which is 8. And if you look at the oxygen on the left, that's going to be true for that one as well. You could also write it this way, where oxygen has, you have 2 pairs of electrons in the middle, and now you can see that each oxygen has the use of 8 electrons. We could do the same thing with nitrogen. But if you look at nitrogen, nitrogen only has 5 electrons. 1, 2, 3, 4, 5. And if I put it next to another nitrogen that has 5, 1, 2, 3, 4, 5, well, these 2 electrons are clearly going to bond together, and these 2 are going to be shared as well, and these 2 up here are going to be shared as well. So what nitrogen does is nitrogen can be written as triply bonded to another nitrogen, or you could write nitrogen as having 6 electrons in the middle and 2 more on each side. So again, nitrogen has the use of 8 electrons. So that's the way we would draw that with Lewis dot diagrams. Now, we need to talk about electronegativities. We've talked about electronegativities before. It's all about strength. Think of a tug of war. Would you like this guy on your team? Yeah, you'd probably win the tug of war. Right? So electronegativities are all about a measurement of an atom's desire for electrons in a chemical bond. How strongly do I want to win? How strongly do I want that electron? That's what this is all about. So if we look at our periodic table, if you remember, electronegativities are the most electronegative element on the periodic table is up here on the right. It's fluorine, and the least electronegative is way down here, which is francium. And you say, well, wait a minute, what happened to the noble gases? They're not over here on the right. Well, the noble gases are not over here, they're not over here on the right because they don't bond for the most part, so we ignore them. So we're not going to worry about them. Okay? Now remember, when we talk about electronegativities, the thing we really want to focus on here are the nonmetals. Right? Because we're talking about covalently bonded substances. So what we're really talking about are the things over here and hydrogen. So let's focus on just them. So I've taken a periodic table, kind of cut it off, and you've only got the nonmetals here, okay? Just because I thought that was easier to work with. And the way electronegativity works is if you have a tug of war, remember we have something that is shared. So in a tug of war, one team can win, one team can lose. But let's say the teams are a little evenly balanced than that. Well, then one team usually is ahead, but sometimes, but can't actually beat the other team. In other words, we can't steal the electron away. So the electron spends more time near the stronger or the more electronegative element. So it's not completely stolen away, like, for example, sodium chloride, where chlorine steals the electron away from sodium. That's not happening here. The two electrons are shared. The more electronegative an element is, the more it's going to want that electron. Okay, so we have two types of covalent bonds. One is called nonpolar covalent and one's called polar covalent. And I'll warn you, sometimes we don't even bother saying covalent. Sometimes we just call them nonpolar and polar. And the reason for that is the covalent is implied, because we can't have a nonpolar ionic molecule. If it's ionic, it's ionic. Okay, so polar simply means they're still shared. Okay, so we have something that is nonpolar covalent when atoms have similar electronegativities, or in fact the same electronegativity, right? And they share a bond, they share electrons, and the shared electrons are equally shared. So both ends of the bonds have similar charges, and when the electronegativity difference is less than 0.5, that tells us we have something that is in fact nonpolar covalent. Okay, so let's look at an example. If we look at F2, this is fluorine bonded to fluorine. Now, if fluorine is bonded to fluorine, where do those electrons stay? Well, if you'll notice, anything bonded to itself, it's going to have the same electronegativity. It's kind of like two twins having a tug of war. Well, the electrons are going to stay right here in the middle. So if I look at fluorine and I look at those two electrons, they're pretty much going to stay right in the middle, the two electrons that are shared. Okay? The same thing is true for chlorine. I'm not going to draw all the stupid electrons, but the electrons are going to kind of sit in the middle. If I have carbon bonded to hydrogen, and I'll just look at one of those bonds, right? Carbon is 2.5 and hydrogen is 2.1. I'm looking at these numbers for electronegativities here, 2.5 and 2.1. Their difference is 0.4. Well, the electrons will spend a little bit of time, a little bit more time with carbon, but not much at all. Not enough to turn this bond into a polar bond. Not enough to have the electrons go over here enough so that this is really negative and that's really positive. Okay, so we view these as non-polar covalent. But what happens if our difference is bigger? When atoms with a significantly different electronegativity share a bond, the shared electrons are more strongly attracted to the atom that is more electronegative. Now, of course, this really is a scale, because if you have an electronegativity difference of 0.5, that's only slightly bigger than 0.4. That didn't make much difference. But if you have something that's up around 2, that's huge. That's a huge difference. In fact, that's almost ionic. All right. So if our electronegativity difference is between 0.5 and 2, this creates a charge in the bond. Now remember, the electron is not completely going over to the other thing. It's still shared. It just spends more time with the other thing. So if I look at HCl and I look at the two electrons that are shared between hydrogen and chlorine, and I'm only drawing those two, all right, well, chlorine has a 3.0 electronegativity and hydrogen has a 2.1. So my difference here is 0.9. Now, realize I'm not worried about negative 0.9, positive 0.9. I'm only looking at the absolute value of the difference is 0.9. These electrons are going to spend more of their time with the most electronegative element. So these electrons are going to spend more time over here than they do in the middle. Now, are they going to spend some time in the middle? Yes. Are they going to spend some time next to hydrogen? Yes, because they're shared, but they're going to spend more time over near chlorine. When that happens, that gives chlorine a slightly negative charge, and it gives hydrogen a slightly positive charge. Now, chlorine did not steal the electrons, in which case it would have a negative charge. It's only slightly that way. Right? If I look at water, I realize you don't know how to draw this yet, but you will eventually. Hydrogen again is 2.1, we already know that, and oxygen is 3.5, so here our difference is even bigger. Here our difference is 1.4. Right, so it's significantly different. Right? So again, our electrons are going to spend more time next to oxygen than they do next to hydrogen, which is going to leave a center of charge back here that is slightly positive, and it's going to leave a charge up here by the oxygen that is slightly negative. How about silicon dioxide? Well, silicon dioxide is actually sharing 4 electrons with oxygen on each side. Again, I'm not worried that you can draw that right now. We'll get there. right? But notice that your difference is silicon is 1.8 and oxygen is 3.5. So that's giving you a difference of, what is it, 1.7 maybe? So, and oxygen has the bigger number. So my electrons are going to spend more time out by oxygen. So that puts a slightly negative charge out here and a slightly negative charge on this end, and it's going to give me a slightly positive charge in the middle. Now again, the electrons don't spend all their time with oxygen. That would be ionic. Okay, this is still polar covalent. We end up with a positive charge in the middle and a negative charge on each end. Alright, we have another term which is called a dipole. A dipole is simply another name for a polar molecule. In other words, if it has a positive and a negative end to it, it's called a dipole. Alright, so whenever we have an unequal sharing of electrons, for example, hydrogen to fluorine, hydrogen is 2.1. Hydrogen is 2.1 and fluorine is 4.0. So my difference here is 1.9. My electrons are going to spend a lot more time with fluorine than they do over with hydrogen. Okay, so we get a definite negative charge. It's still a slightly negative one. We didn't steal the electron, all right, but we're coming pretty close to it. Okay. All right. So we have 2 pages of summary here. Just remember that covalently bonded things are called molecules. That's important. Not ionic, not metallic. Covalently bonded things are called molecules. Valence electrons are shared. They are not given, they are not taken, they are shared. If they're shared equally, we have a polar bond. If they are shared unequally, we have, let me make sure I said that right. If they're shared equally, we have a non-polar bond. And if they're shared unequally, we have a polar bond. So you need to make sure you get those right. And polar molecules are also called dipoles. And you should also know that if your electronegativity difference is 0.4 or less, it's nonpolar covalent. Again, sometimes called nonpolar without the word covalent. If your electronegativity difference is 0.5 to 2.0, you have polar covalent. If it's greater than that, typically it's ionic. But again, the easiest way to tell is if you have a nonmetal and a metal together, that's going to be ionic. Plain and simple. Don't even think about it. Don't look for an electronegativity difference. Metal to nonmetal is ionic. If they're both metals, they're covalent. Then you figure out if it's polar or nonpolar. Okay? Do the worksheet. Hope you took some notes. If you have questions, see you in class, and let me know what you've got. We'll see you soon. Bye.